above your head every single day. The atmosphere performs a transformation so vast that it covers half the planet at once. Oceans of blue appear from invisible air. Sunsets ignite in red and gold. Twilight slowly erases the world into darkness. And then, by morning, it begins again. Most people call it ordinary, but the changing sky is one of the most precise and beautiful demonstrations of physics on Earth. It reveals the motion of our planet, the chemistry of the atmosphere, the path of sunlight through space, and the hidden particles drifting high above us. Every color overhead is information. Every sunrise is an experiment in light. Every sunset is a map of the air. In this documentary, we will uncover why the sky is blue, why violet disappears, why storms can turn green, why mountains darken the sky, and how volcanoes can change sunsets across the world. If thoughtful science documentaries help you relax, learn, or sleep, subscribe to Physical Depth, like this video, and share it so more people can discover the quiet science happening above them every day. Now, before the next sunset arrives, let us understand what the sky has been trying to show us all along. Each morning, before most daily routines begin, one of the largest visual transformations on Earth quietly takes place. The sky, which may have been dark only an hour earlier, begins to brighten. Faint gray tones give way to pale blue. Near the horizon, warm colors may briefly appear, soft yellow, orange or pink, before fading into the broader light of day. By noon, the same sky often seems clear, bright and stable. Later, as evening approaches, the process reverses. Blue gradually softens. Gold and red return. Then darkness settles again. Because this sequence happens every day, it is easy to overlook. Human perception is highly efficient at ignoring familiar patterns. Repeated events become background information, noticed only when something changes. A dramatic sunset may capture attention. A storm-darkened afternoon may feel unusual. Yet the ordinary transition from dawn to noon to dusk contains complex physical processes unfolding continuously above every landscape. The changing color of the sky is not caused by the sky itself, because the sky is not a painted dome or a solid surface. It is the visible result of sunlight interacting with Earth's atmosphere. Invisible gases, microscopic particles, water droplets, and shifting layers of air influence how light travels. As the position of the sun changes through the day, the path taken by that light also changes. With each change in angle, different colors are scattered, absorbed, or redirected toward the observer. This means the sky is never truly static. Even on a cloudless day, it is in motion as an optical system. The blue above noon is not identical to the blue of early morning. The brightness near the horizon differs from the brightness overhead. Seasonal humidity, airborne dust, pollution, and altitude can all subtly alter the scene. What appears simple is therefore the product of geometry, atmospheric chemistry, and the behavior of light itself. A familiar glance upward contains evidence of planetary structure and solar illumination working together in real time. To understand why the sky changes color every day, it is first necessary to notice that it is always changing. When people look upward, the sky often appears as a smooth ceiling stretched above the landscape. It can seem like a distant surface painted in blue during the day and black at night. This impression is understandable. Human vision naturally interprets broad fields of color as boundaries or backgrounds. Yet the sky is neither a wall nor a dome. It is a visual effect produced by looking through a vast volume of atmosphere. Earth's atmosphere extends upward for hundreds of kilometers, gradually thinning with height. Most of its mass, however, is concentrated close to the ground. The air surrounding mountains, oceans, forests, and cities forms layers of gas held in place by gravity. Nitrogen and oxygen dominate this mixture, with smaller amounts of argon, carbon dioxide, water vapor, and trace compounds. Suspended within it are dust grains, sea salt, pollen, soot, droplets, and ice crystals. Though often invisible individually, together they shape the appearance of the sky. When sunlight enters this envelope of air, it does not simply pass straight through untouched. Countless molecules and particles interact with the incoming light. Some wavelengths are scattered in many directions, some are weakly absorbed. Some continue forward, while others are redirected toward the eyes of an observer standing below. What we call the sky is the combined light arriving from every visible direction after these interactions have taken place. Because of this, the sky has depth. Looking overhead means looking through a shorter column of air than looking toward the horizon. Near the horizon, the line of sight passes through a much longer path of atmosphere. That longer path contains more molecules, more particles, and more opportunities for scattering. This is one reason the horizon often appears paler, whiter, or warmer than the deeper blue overhead. The sense of distance in the sky is also unusual, because there is no clear surface for the eye to focus upon. Clouds can provide reference points, but clear air does not. The result is an immense visual volume with few boundaries, where color is suspended rather than attached to an object. Understanding this changes the question entirely. We are not asking why a surface changes color. We are asking why sunlight changes appearance while traveling through a layered ocean of air. The sky is not above us as an object. We are already inside it. Color often feels like a permanent property of the world. Leaves seem green, oceans seem blue, stone appears gray, and evening clouds glow orange. Yet color does not exist as an independent substance stored inside objects or suspended in the air. Color emerges only when light interacts with matter and is then interpreted by a visual system. Without light and without perception, color as humans experience it does not appear. Sunlight contains a broad range of electromagnetic wavelengths. A small portion of that spectrum is visible to human eyes. These visible wavelengths are commonly described as violet, blue, green, yellow, orange, and red, though in reality, they form a continuous gradient rather than separate bands. Each wavelength carries energy and travels through space, but none of them are inherently colored in the human sense. Color is the brain's interpretation of incoming signals generated by these wavelengths. Inside the human retina are specialized cells called cones, sensitive to different regions of the visible spectrum. When light enters the eye, these cells respond in overlapping patterns. The brain compares those responses and constructs the sensation of color. What appears as blue sky or red sunset is therefore a neurological experience built from physical input. This also explains why color changes with conditions. The same object can appear different under morning sunlight, indoor lighting, or twilight. A white surface under warm evening light may look golden, Under shade, it may seem cool and blue. The material itself may remain unchanged, but the light reaching it has shifted, and perception adjusts accordingly. The sky offers one of the clearest examples of this principle. There is no blue pigment spread across the atmosphere. Air molecules are colorless at ordinary scales. Instead, sunlight entering the atmosphere is redirected in ways that favor certain wavelengths. Those wavelengths then reach the eye from many directions, and the brain interprets that pattern as blue. Different species perceive this process differently. Many birds can detect ultraviolet wavelengths invisible to humans. Some animals have fewer color receptors and experience a narrower visual world. This means the sky we describe is specifically a human sky, shaped by human sensory biology. To understand why the sky changes color each day, we must recognize that color is a relationship. It depends on light, matter, and the observer meeting at the same moment. Sunlight often appears simple. To the eye, it can seem white, uniform, and constant. It illuminates landscapes, warms surfaces, and defines the cycle of day. Yet, this apparent simplicity hides a more complex structure. Sunlight is not made of a single type of light. It is a blend of many wavelengths, traveling together from the sun, through space, and into Earth's atmosphere. The sun produces energy through nuclear fusion in its core, where hydrogen atoms combine under immense pressure and temperature. This energy moves outward over long timescales, eventually reaching the solar surface and radiating into space. Part of that radiation falls within the narrow range visible to human vision. These visible wavelengths span from shorter violet and blue light to longer orange and red light, with green, yellow, and intermediate tones between them. When many visible wavelengths arrive together in balanced proportions, the human eye usually interprets the result as white light. This is why direct sunlight at midday often appears nearly white. It contains a broad spectrum rather than a single color. The same principle can be demonstrated when sunlight passes through a prism or water droplets in the atmosphere. Different wavelengths bend by slightly different amounts, separating into the familiar sequence of rainbow colors. This range matters because each wavelength interacts differently with matter. Shorter wavelengths, such as blue and violet, are scattered more easily by tiny gas molecules in the atmosphere. Longer wavelengths, such as red and orange, tend to continue more directly through clear air. Because sunlight is a mixture, the atmosphere can selectively redistribute parts of it while leaving others less affected. The balance of wavelengths reaching the ground is therefore never identical throughout the day. When the sun is high overhead, its light passes through a shorter path of atmosphere. More of the original mixture remains intact. When the sun is low near sunrise or sunset, the light must travel through much more air. Shorter wavelengths are scattered away from the direct beam, leaving warmer tones more prominent. Even beyond visible light, sunlight includes ultraviolet radiation, infrared energy, and other wavelengths outside human perception. The sunlight we see is only one narrow window within a larger spectrum. To understand the changing sky, it is essential to begin here. Daylight is not one color arriving from one source. It is many wavelengths, constantly sorted by the atmosphere above us. Earth's atmosphere is often described as air, weather, or climate. It is the medium through which birds fly, clouds form, and winds move across continents. Yet from the perspective of light, the atmosphere is also something else, a vast optical system in constant motion. Every day, Sunlight passes through this system and is subtly altered by it. An optical medium is any material through which light travels and within which light can be redirected, scattered, absorbed, or bent. Glass lenses, water, and crystal are familiar examples. Air may seem too transparent to belong in the same category, but transparency does not mean inactivity. Even clear air contains molecules, suspended particles, temperature gradients, and changing densities that influence the path of incoming light. The atmosphere is composed mainly of nitrogen and oxygen, with smaller amounts of argon, carbon dioxide, and water vapor. These gases are not evenly arranged in a fixed structure. Pressure decreases with height. Temperature rises and falls in layers. Moisture collects, condenses, and evaporates. Winds transport dust from deserts, salt from oceans, smoke from fires, and pollutants from cities. The result is a dynamic medium whose optical properties vary from place to place and hour to hour. When sunlight enters this shifting environment, billions of interactions occur continuously. Molecules scatter shorter wavelengths more efficiently than longer ones. Larger particles produce softer, less selective scattering. Water droplets and ice crystals can reflect, refract, or diffuse light. Gradients in air density can bend light slightly, contributing to mirages and shimmering horizons. Because the atmosphere is moving, the sky is never visually identical from one day to the next. A dry, clean air mass may produce deep blue clarity. Humid conditions can create a pale or milky sky. Smoke from distant wildfires may intensify sunsets by filtering shorter wavelengths. Fine dust lifted high into the air can alter color over entire regions. Even on calm days, convection currents rise from warm ground while colder air sinks elsewhere. Layers mix slowly. Invisible motion continues overhead. The apparent stillness of the sky often conceals continuous physical exchange. Seen this way, the atmosphere is not empty space between Earth and the Sun. It is an active filter, lens, and scattering field wrapped around the planet. The colors of each day are the visible expression of that moving optical medium at work. Each day begins with a transfer of energy across space. Long before sunlight reaches the ground, it has already traveled approximately 150 million kilometers from the Sun to Earth. This journey takes a little more than 8 minutes. Moving at the speed of light through near vacuum, solar radiation crosses interplanetary space largely uninterrupted. Only when it meets Earth's atmosphere does the character of that journey begin to change. From orbit, the planet appears wrapped in a thin, luminous shell. Compared with Earth's diameter, the atmosphere is shallow, yet it plays an outsized role in shaping daylight. Incoming sunlight first encounters the highest, rarest layers of gas, where molecules are sparse and collisions are infrequent. Here, some energetic ultraviolet radiation is absorbed, particularly by ozone in the upper atmosphere. This absorption protects surface life while also warming certain atmospheric layers. As the light continues downward, the air becomes denser. Molecules of nitrogen and oxygen become more numerous, and the chance of interaction rises sharply. At this stage, some photons continue directly toward the surface, while others are scattered in new directions. Instead of a single beam moving straight downward, sunlight begins to spread through the atmosphere, filling the sky with diffuse illumination. Not all wavelengths behave equally during this descent. Shorter wavelengths are more readily redirected by tiny gas molecules, while longer wavelengths tend to preserve a straighter path. This selective scattering is one of the central reasons daylight skies appear blue and low-angle sunlight appears warm. The atmosphere does not create new colors, it redistributes the mixture already present in sunlight. It stables. Clouds and aerosols add further complexity. Fine dust, sea salt, smoke, pollution particles, and droplets of water can reflect and scatter light more broadly. In humid air, the incoming light may soften and lose contrast. In dry conditions, it can appear sharper and more transparent. The angle of arrival also matters. When the sun stands high, its rays pass through a shorter atmospheric path. Near sunrise or sunset, the same light enters at a shallow angle and travels through much more air before reaching the observer. This longer route increases scattering and filtering. By the time sunlight reaches the ground, it is no longer exactly the light that left space moments earlier. It has been sorted, diffused, diminished, and redirected by a planetary envelope of gas. The sky we see is the record of that journey. To understand why the daytime sky becomes blue, it is useful to look at a scale far below ordinary human experience. The atmosphere appears continuous and empty when viewed from the ground, but it is composed of countless individual molecules moving rapidly in all directions. Most of these are nitrogen and oxygen, each far too small to be seen directly. Their size is central to how they interact with sunlight. Visible light travels in wavelengths, measured in nanometers. Red light has longer wavelengths, while blue and violet light have shorter ones. Although all visible wavelengths are extremely small by everyday standards, they are still much larger than the dimensions of individual gas molecules. A nitrogen or oxygen molecule is tiny compared with the span of a visible light wave. This mismatch in scale creates a specific kind of interaction. If particles in the atmosphere were much larger, such as droplets or coarse dust, they would scatter light differently and less selectively. But molecules smaller than the wavelength of visible light respond to incoming electromagnetic waves in a way that strongly favors shorter wavelengths. The electric field of the passing light causes the molecule's charges to oscillate briefly, and the molecule then re-radiates light outward in multiple directions. Because smaller wavelengths stimulate this response more efficiently, blue and violet light are scattered much more strongly than red light. This means that when sunlight enters clear air, the shorter wavelength portion of the spectrum is redirected across the sky, while longer wavelengths remain more concentrated in the direct path from the sun. The atmosphere contains an immense number of these molecules. A single cubic centimeter of air near sea level contains billions upon billions of them. Even though each interaction is minute, their combined effect across kilometers of atmosphere becomes visually dominant. The sky fills with scattered light, arriving from every direction. This process depends on the air remaining relatively clear. When larger particles, such as smoke, pollution, or thick haze become abundant, their influence can overwhelm molecular scattering and mute the deep blue of a clean sky. What seems like empty space is therefore a structured field of microscopic scatterers. The molecules are individually insignificant, yet collectively they determine the color overhead. The blue sky begins not with clouds or pigment, but with matter so small it can only be understood through physics. The blue color of the daytime sky is primarily explained by a process known as Rayleigh scattering. Named after the 19th century physicist Lord Rayleigh, this principle describes how light is scattered by particles much smaller than the wavelength of the light itself. In Earth's atmosphere, The relevant particles are mostly nitrogen and oxygen molecules. When sunlight enters the atmosphere, it carries many visible wavelengths together. If no atmosphere existed, the sun would appear against a black sky even during daytime, because there would be no material to redirect light across the heavens. Instead, Earth is surrounded by trillions of microscopic molecules. As incoming light passes among them, the oscillating electric field of the light briefly disturbs the electric charges within each molecule. Those molecules then emit light outward in multiple directions. Rayleigh scattering is strongly dependent on wavelength. The intensity of scattering increases rapidly as wavelength becomes shorter, approximately following an inverse fourth power relationship. In practical terms, blue light is scattered many times more efficiently than red light. Violet light, with even shorter wavelengths, is scattered strongly as well, though other factors influence what we ultimately perceive. Because of this preference, the shorter wavelength portion of sunlight is redistributed throughout the atmosphere. Instead of remaining concentrated only in the direct beam from the sun, blue-rich light arrives from all visible directions. When we look away from the sun toward the open sky, we are seeing sunlight that has been scattered sideways and downward through the air. Longer wavelengths, such as red and orange, are less easily scattered by molecules. They continue more directly through the atmosphere, especially when the sun is high. This helps preserve the sun's bright near-white appearance at midday, while the surrounding sky becomes blue. The strength of Rayleigh scattering also depends on the amount of atmosphere the light passes through. A thicker path means more opportunities for scattering. This is why the sky often changes tone from horizon to zenith, and why warm colors emerge more strongly when the sun is low. Rayleigh scattering is not an isolated curiosity. It is one of the defining optical behaviors of a gaseous planet under sunlight. Every clear day, without noise or announcement, the atmosphere sorts incoming light by wavelength. The result is the calm blue canopy, so familiar that it is often mistaken for something permanent rather than something continuously produced. If shorter wavelengths of light are scattered more strongly by Earth's atmosphere, an obvious question follows. Violet light has a shorter wavelength than blue light, so by the logic of Rayleigh scattering, it should be redirected even more efficiently. If this is true, then why does the daytime sky usually appear blue rather than violet? The answer lies not in a single cause, but in several overlapping factors involving sunlight, atmospheric filtering, and human vision. Rayleigh scattering does indeed favor violet wavelengths strongly. However, the amount of violet light available in incoming sunlight is lower than the amount of blue and nearby wavelengths. The sun emits a broad spectrum, but not every visible region arrives at Earth in equal strength. In addition, part of the violet and ultraviolet portion of solar radiation is absorbed in the upper atmosphere. Ozone plays an important role in filtering energetic short wavelengths before they reach lower layers of air. While visible violet is not removed entirely, the available intensity is reduced compared with what would otherwise enter the scattering process. Human perception adds another decisive layer. The retina contains cone cells that respond to different regions of the visible spectrum. But our eyes are not equally sensitive to all wavelengths. Human vision is relatively weak in the far violet range and more responsive to blue-green regions. Even when violet light is physically present, it does not produce as strong a perceptual signal as wavelengths closer to blue. The sky's color is therefore a combined sensory average rather than a direct reading of one wavelength alone. Scattered light from the atmosphere includes a mixture of violet, blue, and nearby tones. The brain integrates these signals and interprets the result as blue. Atmospheric conditions can shift this balance further. Haze, aerosols, humidity, and pollution often soften shorter wavelengths, making the sky paler or less saturated. At high altitudes, in exceptionally clear air, some skies can appear deeper and slightly more violet blue than usual. This question reveals an important principle. Nature is not always explained by one rule in isolation. Physics determines how light is scattered, chemistry influences what survives the journey, and biology shapes what is perceived. The sky appears blue not because violet is absent, but because the final color emerges from the combined effects of sunlight, atmosphere, and the limits of human sight. On many clear days, the sky overhead appears deeper and darker blue than the sky near the horizon. The contrast can be subtle or pronounced, depending on weather, season, and location. Near the horizon, the sky often looks paler, brighter, or slightly whitish, while the zenith, the point directly above the observer, holds a richer tone. This gradient is so common that it is often accepted without question, yet it reveals important differences in how light travels through the atmosphere. The first reason is geometric. Looking straight upward means looking through a shorter column of air. Looking toward the horizon means the line of sight passes sideways through a much longer path of atmosphere before reaching distant space. Even though the atmosphere thins with altitude, the horizontal viewing path still contains far more molecules and suspended particles than the vertical one. That longer path increases scattering and mixing. Light arriving from the horizon has undergone more interactions before reaching the eye. In addition to blue wavelengths scattered by molecules, there is often a greater contribution from larger particles, such as dust, water droplets, pollution aerosols, and fine haze. These larger particles scatter light more evenly across wavelengths, producing a washed or milky brightness that reduces the apparent depth of blue. The horizon also receives light from many directions near Earth's surface. Reflections from land, water, buildings, vegetation, and cloud layers can brighten lower parts of the sky. Moisture and airborne particles tend to be more concentrated in the lower atmosphere, especially close to populated or humid regions, further softening color. By contrast, when looking toward the zenith, the visual path is shorter and often passes through cleaner, thinner air. There is less accumulated haze and less whitening from broad scattering. The remaining scattered light is therefore more strongly dominated by molecular processes that favor blue wavelengths, creating a darker and more saturated appearance. Solar position matters as well. During midday, the effect is often strongest because the sun is high and overhead regions are brightly supplied with scattered blue light, while horizon parts remain long. Near sunrise or sunset, the entire gradient changes as sunlight enters at shallow angles. The sky's uneven color is not a flaw or inconsistency. It is a map of atmospheric depth. The darker zenith and paler horizon show that the air above us is not visually uniform, but a layered optical volume shaped by distance, particles, and light. By midday, the sky around the sun is often blue, shaped by the scattering of shorter wavelengths through the atmosphere. Yet the sun itself usually appears bright white or only slightly yellow. This may seem contradictory. If blue light is being scattered away into the sky, why does the direct sunlight still retain a nearly neutral color? The answer begins with the broad spectrum of sunlight. Sunlight contains many visible wavelengths together, from shorter blue tones to longer red ones, along with intermediate greens and yellows. When these wavelengths arrive in relatively balanced proportions, the human visual system interprets the mixture as white light. The atmosphere modifies this balance, but at noon, it often does so only modestly, along the direct path from the sun to the observer. When the sun is high overhead, its rays travel through a shorter thickness of atmosphere than during sunrise or sunset. This shorter path means fewer opportunities for scattering and absorption before the light reaches the ground. Some blue wavelengths are redirected into the surrounding sky, but not enough to remove them completely from the direct solar beam. Much of the original spectral mixture remains intact because the remaining light still includes substantial contributions across the visible range. The sun continues to appear nearly white. Any slight reduction in blue may shift perception toward a faint warm tint, especially in hazy conditions, but the overall impression is usually neutral because the brightness of the sun is extremely intense compared with most other objects in view. Human vision also adapts strongly to bright illumination. The eye and brain continuously adjust to changing light levels, helping maintain stable color perception under different conditions. This process, known as color constancy, contributes to the sun's familiar white appearance during daytime, even as atmospheric filtering subtly changes its spectrum. Near sunrise or sunset, the situation changes. The sun's light must cross a much longer atmospheric path, allowing far more short wavelengths to be scattered away. Reds and oranges then dominate the direct beam, and the sun can appear warm, amber, or deep red. At noon, however, the atmosphere acts more like a light editor than a severe filter. It redistributes part of the blue into the sky, while allowing most of the mixed spectrum to continue downward. The result is a common but elegant contrast: a blue sky surrounding a sun that still shines almost white. Not all scattering in the atmosphere comes from tiny gas molecules. The blue sky of clear air is largely shaped by Rayleigh scattering, which occurs when particles are much smaller than the wavelength of visible light. But Earth's atmosphere also contains larger suspended particles: dust, sea salt, smoke, soot, pollen, industrial emissions, and microscopic droplets. When light interacts with particles closer in size to the wavelength of light, a different process becomes important: Mie scattering. Named after physicist Gustav Mie, this form of scattering behaves differently from molecular scattering. It is less selective by wavelength, meaning it does not strongly favor blue light over red light. Instead, many visible wavelengths are scattered more evenly. As a result, air rich in aerosols often appears pale, whitish, or gray, rather than deep blue. These particles come from many sources. Winds lift mineral dust from dry soils and deserts, carrying it across oceans and continents. Breaking waves release sea salt into coastal air. Wildfires inject smoke into the atmosphere. Cities contribute soot, sulfates, nitrates, and other fine pollutants. Vegetation releases organic particles and pollen. Even in remote places, the atmosphere is rarely composed of gases alone. Because Mie scattering affects multiple wavelengths similarly, it tends to soften contrasts in the sky. Distant mountains may fade into bluish-gray haze. Horizons become brighter and milkier. The sharp saturation of a clean, dry sky can be replaced by a muted brightness spread across large areas. This type of scattering also sends a significant amount of light forward. That means sunlight passing through hazy air can create glare around the sun or a washed appearance near bright regions of the sky. On humid days, when tiny water droplets join other aerosols, this effect often becomes stronger. Mist scattering plays an important role in sunrise and sunset colors as well. Aerosol-rich air can intensify warm tones by removing or diffusing shorter wavelengths along long atmospheric paths. Under some conditions, it produces vivid orange skies. Under others, it simply dulls the scene. The atmosphere, then, is not a pure gas chamber, but a suspension of constantly changing particles. Their presence alters how daylight spreads through the air from one hour to the next. When the sky looks white, hazy, or softly luminous instead of clear blue, it is often the signature of dust, salt, and aerosols quietly reshaping the light. Clouds often appear white, though they are made of water droplets or ice that are themselves nearly colorless. At times, they can also look gray, silver, or softly gold in changing light. To understand these shifting appearances, it is useful to consider how clouds interact with sunlight differently from clear air. The blue sky is mainly produced by scattering from tiny gas molecules, which are much smaller than the wavelengths of visible light. Clouds, however, are composed of droplets and ice crystals far larger than individual wavelengths. Typical cloud droplets are many times wider than visible light waves. Because of this size difference, they scatter sunlight through processes dominated by broad, multi-wavelength interactions, rather than the selective preference for blue seen in Rayleigh scattering. When white sunlight enters a cloud, it encounters countless droplets suspended through a three-dimensional volume. Light is reflected, refracted, and scattered repeatedly from one droplet to another. Since the droplets are large relative to wavelength, they redirect red, green, and blue portions of sunlight in more comparable amounts. When these colors reach the eye together, the result is perceived as white. A bright white cloud, therefore, indicates that much of the incoming sunlight is being scattered back outward efficiently. Thick cumulus clouds on sunny afternoons often show this effect strongly, with brilliant sunlit tops and softer shaded interiors. The cloud is not emitting white light of its own. It is redistributing the sun's full visible spectrum. Gray clouds form when less light escapes toward the observer. In thick or dense clouds, sunlight may be scattered many times, absorbed slightly, or blocked by upper layers before reaching lower regions. The underside then receives reduced illumination and appears darker. Storm clouds can become deep gray when water content is high and light penetration is limited. Clouds also take on color when the sunlight entering them has already been altered by the atmosphere. Near sunrise or sunset, direct sunlight becomes richer in reds and oranges after shorter wavelengths are scattered away along the long path through air. Clouds illuminated by that warm light reflect those tones, producing pink, gold, or crimson edges. Because clouds are large collections of droplets moving through changing air, their brightness and color can shift minute by minute. Shape, thickness, angle to the sun, and surrounding atmosphere all matter. A cloud is therefore not a painted object in the sky. It is a suspended field of water and ice that gathers many colors of sunlight and returns them together. On some days, the sky appears deep and sharply blue. On others, that same sky becomes pale, washed, or softly white near the horizon. Distant hills lose contrast, city skylines fade, and sunlight seems diffused rather than crisp. This change is often caused by haze, a common atmospheric condition created by fine suspended particles and microscopic droplets that alter how light moves through the air. Haze is not usually a solid layer like a cloud. It is a thin distribution of aerosols spread through lower and middle parts of the atmosphere. These particles may include dust, sea salt, smoke, sulfates, organic compounds, industrial pollution, and tiny water droplets formed in humid air. Individually, they are small, but collectively they can strongly influence visibility and color. In clear conditions, the blue sky is dominated by Rayleigh scattering from gas molecules, which preferentially scatter shorter wavelengths. This selective process gives the atmosphere its rich blue appearance. When haze increases, larger particles begin to contribute more strongly through Mie scattering. Unlike molecular scattering, Mie scattering is less selective by wavelength and tends to redirect many colors more evenly. The result is a whitening effect. Instead of seeing mainly blue, rich, scattered light, the observer receives a broader mixture of wavelengths. The sky then looks lighter, grayer, or milkier. Blue remains present, but it is diluted by additional scattered reds, greens, and yellows. Haze also reduces contrast across long distances. Light traveling from mountains, buildings, or forests to the eye must pass through particle-filled air. Along the way, extra scattered light is added, while some directional detail is lost. This causes distant objects to appear faint and bluish-gray, a phenomenon long recognized in landscape painting and atmospheric science alike. Humidity often intensifies haze because many aerosol particles attract water. As they absorb moisture, they grow larger and scatter light more effectively. This is why warm, humid days can feel visually softer, even without cloud cover. The effect is usually strongest near the horizon, where the line of sight passes through a longer path of atmosphere. Overhead, where the path is shorter, some deeper blue may remain visible. Haze does not remove the sky, it blends it. By adding countless small scatterers to the air, the atmosphere shifts from transparent depth toward luminous softness, turning the blue of day into something quieter and less defined. The light that reaches the ground is never determined by sunlight alone. Between the sun and the observer lies an atmosphere whose composition changes from hour to hour. Two of the most influential variables in everyday life are humidity and pollution. Both are often invisible at first glance, yet both can reshape brightness, color, contrast, and the overall mood of the sky. Humidity refers to the amount of water vapor present in the air. Water vapor itself is transparent, but humid air frequently supports the growth of microscopic droplets and water-coated aerosol particles. Many airborne particles attract moisture, swelling, as humidity rises. Once enlarged, they scatter light more efficiently. The result is often a softer sky, brighter haze near the horizon, and reduced clarity over distance. On dry days, sunlight can feel sharper, shadows appear more defined, distant landscapes stand out with stronger contrast, and the blue overhead may deepen. In dry air, there are often fewer droplets and less broad scattering from moisture-laden particles. Molecular scattering remains prominent, allowing cleaner blue tones to dominate. Pollution introduces another layer of complexity. Urban and industrial activity can release sulfates, nitrates, soot, volatile organic compounds, and fine particulates into the atmosphere. Vehicles, power generation, construction, biomass burning, and domestic heating all contribute depending on region and season. These particles interact with light through scattering and, in some cases, absorption. Some pollutants brighten the sky by diffusing sunlight, producing a pale or whitish appearance. Others, especially darker carbon-rich particles, absorb portions of incoming light and can dim the atmosphere or alter color balance. When concentrations are high, the sun may appear muted, and distant features can disappear into gray layers. Humidity and pollution often reinforce one another. Polluted air in humid conditions can generate especially dense haze because many particles serve as nuclei for water uptake. This combination is common in urban basins and coastal cities, where still air can trap aerosols close to the surface. These effects are not limited to daytime blue. Evening colors can intensify when suspended particles scatter shorter wavelengths from long solar paths, allowing oranges and reds to become more visible. Under different mixtures, sunsets may instead look dull and brownish. The changing character of light is therefore a daily atmospheric report. Crisp blue skies, soft white haze, muted noon sunlight, or glowing sunsets each reflect the state of the air through which light has traveled. The color of daylight depends not only on the composition of the atmosphere, but also on the route sunlight must take through it. One of the most important changes during each day is geometric rather than chemical. As Earth rotates, the apparent position of the sun rises and falls across the sky. This alters the angle at which sunlight enters the atmosphere, and with that change, the distance light must travel through air before reaching the observer. When the sun is high near midday, incoming rays pass more directly downward. Their path through the densest lower atmosphere is relatively short. Light encounters fewer molecules, fewer aerosols, and fewer opportunities for scattering or absorption. Much of the original mixture of wavelengths remains in the direct beam, which is why noon sunlight often appears bright and nearly white. As the sun moves lower toward the horizon, the geometry changes. Sunlight now enters at a shallow angle, crossing sideways through a much longer slice of atmosphere. Though the atmosphere gradually thins with altitude, the total distance through air increases dramatically. This longer route means that photons are more likely to interact with molecules, dust, water droplets, and suspended particles many times before arriving at the ground. The effect can be described using the concept of air mass, a measure of how much atmosphere sunlight passes through relative to the overhead path. Near midday, the air mass is close to 1. At lower solar angles, it increases several times over, especially near sunrise and sunset. With each additional layer of air, selective filtering becomes stronger. Shorter blue and violet wavelengths are scattered away from the direct solar beam more efficiently than longer red and orange wavelengths. As the path length grows, more of these shorter wavelengths are removed from the sunlight traveling straight toward the observer. The remaining light becomes progressively warmer in tone. Longer atmospheric paths also magnify the influence of local conditions. Dust, smoke, pollution, volcanic aerosols, or humid haze can intensify filtering and dramatically change the appearance of dawn and dusk. The same sunset angle can produce gentle pastel tones one day and deep crimson the next. This daily shift requires no weather front or storm system. It is built into Earth's rotation itself. Every evening and morning, the planet quietly changes the thickness of air through which sunlight must pass. The warm colors of low sun begin with a simple fact of geometry. Light has farther to travel. When the sun approaches the horizon, its light no longer takes the short, direct route typical of midday. Instead, It travels through a far longer section of Earth's atmosphere before reaching the observer. Along this extended path, one of the most important changes is the gradual removal of shorter wavelengths, especially blue light, from the direct beam. Sunlight begins as a broad mixture of visible wavelengths. In open space, these wavelengths travel together without significant separation. Once the light enters the atmosphere, however, molecules of nitrogen and oxygen begin to scatter the shorter wavelengths more efficiently than the longer ones. This selective process operates throughout the day, but it becomes far more noticeable when the path through air increases. Near the horizon, sunlight may pass through several times more atmosphere than it does at noon. Every additional layer provides more opportunities for blue and violet wavelengths to be redirected away from the incoming beam. Some of that scattered blue light contributes to the surrounding sky. Some is scattered multiple times and diffused through the atmosphere. What matters to the observer looking toward the sun is that less blue remains in the light arriving directly from that direction. This does not mean blue light is destroyed. It is redistributed. The atmosphere acts less like a sponge and more like a sorting system, sending shorter wavelengths outward while allowing longer wavelengths to continue more efficiently along the original path. As the blue component is progressively reduced, the balance of the remaining sunlight shifts. Yellow, orange, and red wavelengths become proportionally stronger. At first, the sun may appear golden. As the path length increases further, orange deepens and reds can emerge, especially in clear air with moderate aerosols. Conditions near the surface often enhance the effect. Dust, humidity, smoke, and pollution add larger particles that scatter and absorb additional light. These factors can intensify the filtering of shorter wavelengths or soften the scene into muted amber tones. The horizon itself is therefore a region where atmospheric optics become especially visible. It is not the edge of the sky changing color, but the longest daylight pathway through air. Each sunset and sunrise demonstrates the same quiet principle. When sunlight must travel farther, blue is increasingly removed from the direct route, and the warmer colors that were always present become easier to see. The warm colors of sunrise and sunset often feel like something newly created. Red clouds, orange horizons, and golden light seem to appear suddenly at the edges of the day. Yet these colors were present in sunlight all along. What changes is not the existence of red or orange wavelengths, but their relative prominence after the atmosphere has altered the incoming light. Sunlight contains a continuous range of visible wavelengths. During midday, this mixture reaches the ground in comparatively balanced form, so daylight appears white or slightly warm. Shorter blue wavelengths are scattered into the sky, but enough remain in the direct beam that no single warm color dominates. The atmosphere edits the spectrum only moderately when the sun is high. As the sun lowers, the path through air becomes much longer. Along that route, shorter wavelengths such as blue and violet are increasingly scattered away by molecules and suspended particles. With each additional segment of atmosphere, the direct beam loses more of its cool-toned components. What remains is progressively enriched in longer wavelengths. Red and orange light scatter less efficiently than blue, allowing them to continue through the atmosphere more successfully when distances are great. Yellow wavelengths often remain as well, combining with red and orange to produce a broad range of warm tones. Depending on the exact balance, the sun may appear golden, amber, copper, or deep red. The atmosphere can also spread these colors beyond the sun itself. Clouds, haze layers, and airborne particles intercept the warm light and reflect or scatter it across the landscape. This is why distant clouds may glow pink or orange even when the sun is below the horizon. Mountains, buildings, and water surfaces can take on a soft golden cast as they receive light already filtered by long atmospheric travel. Local conditions determine intensity. Clean, dry air may produce delicate yellow and pale orange transitions. Moderate aerosols can enhance dramatic reds by removing more short wavelengths. Excessive pollution or thick cloud may mute the scene into dull brown-gray light. Human perception contributes as well. Against the cooling blue of the upper sky, warm tones near the horizon appear especially vivid through contrast. These evening and morning colors are therefore not separate from daylight. They are the hidden, warmer portion of sunlight, revealed when shorter wavelengths have been scattered elsewhere. Reds, oranges, and golds become visible when the atmosphere lengthens the journey of light and quietly changes which colors remain. Not every sunset ends the day in the same way. Some evenings fill the horizon with layered oranges, deep reds, and luminous pink clouds, visible for long minutes. Other sunsets pass almost unnoticed, fading from pale yellow into gray before darkness arrives. The sun follows the same daily motion, yet the visual outcome can differ greatly. The reason lies in changing atmospheric conditions that determine how light is filtered, scattered, and reflected. The basic mechanism of sunset color remains consistent. As the sun lowers, its light travels through a longer path of atmosphere. Shorter blue wavelengths are increasingly scattered away, allowing warmer tones to dominate the direct beam. This process occurs every clear evening, but the intensity and beauty of a sunset depend on what the sunlight encounters along that extended route. A moderate amount of aerosols often enhance a sunset color. Fine dust, sea salt, smoke, or pollution particles can increase the removal and diffusion of shorter wavelengths, while helping spread warm light across clouds and haze layers. Under these conditions, reds and oranges may intensify and linger across broad portions of the sky. Too few particles can produce a cleaner but subtler sunset. In exceptionally transparent air, the horizon may glow softly with gold and light orange, yet lack dramatic saturation. The atmosphere filters less aggressively, so transitions can remain gentle and understated. Too many particles can also diminish color. Dense pollution, thick smoke, or heavy humidity may scatter and absorb so much light that the sunset becomes dull, brownish, or obscured entirely. Instead of glowing layers, the sun may simply dim behind haze. Cloud structure is equally important. Thin clouds often create some of the most vivid displays because they intercept warm sunlight from below after the sun nears or slips beneath the horizon. Their elevated position allows them to remain illuminated while the ground darkens. Thick, low clouds, by contrast, may block the light before it can spread through the sky. Weather patterns influence all of this. Dry air after a cold front may create clarity. Moist, stagnant air may mute contrast. Dust transported from distant deserts or smoke from remote fires can transform sunsets hundreds or thousands of kilometers away. The observer's location matters too. Coastal humidity, mountain elevation, urban haze, and open plains each shape the view differently. A brilliant sunset is not guaranteed by the setting sun alone. It is the product of a precise atmospheric balance. When that balance is absent, the day often fades quietly instead. As the sun approaches the horizon, evening light begins to travel through a far longer portion of the atmosphere than it does at midday. This extended path reveals features of the air that often remain unnoticed during brighter hours. Thin layers of dust, drifting smoke, and suspended ice crystals can become suddenly visible, not because they appear at sunset, but because low-angle sunlight interacts with them in ways the human eye can easily detect. The atmosphere is rarely uniform from ground to upper sky. Winds move material into distinct layers, separated by temperature, humidity, and altitude. Desert dust may cross oceans in elevated plumes. Smoke from distant wildfires can spread across continents in broad bands. High cirrus clouds composed of ice crystals may form near the upper troposphere, while lower air remains clear. These separate layers respond differently when illuminated from the side by evening sunlight. Dust particles often warm the color of sunsets. As sunlight passes through dusty air, shorter blue wavelengths are increasingly scattered away, allowing oranges and reds to become more prominent. If the dust layer is elevated, it may glow after the lower atmosphere has already dimmed, creating horizontal bands of amber or copper light above the horizon. Smoke can produce similar, but often more complex effects. Fine smoke particles scatter and absorb light efficiently, sometimes deepening reds and magentas when concentrations are moderate. In heavier amounts, smoke may mute the sky into dull orange-brown tones or soften the sun into a dim red disk. The exact outcome depends on particle size, density, and altitude. Ice crystals create another category of evening display. High in cold air, hexagonal crystals within cirrus clouds can reflect and refract sunlight, producing luminous veils, bright edges, and occasionally halos or pillars of light. Because these clouds are elevated, they may remain sunlit long after the ground has entered shadow. This can make the upper sky glow while the landscape below grows dark. The layering of these materials often explains why sunsets have depth. One zone may appear golden, another crimson, another violet blue above it. Each color band corresponds to sunlight interacting with different heights and different particles. Evening light is therefore diagnostic. It reveals the hidden structure of the atmosphere. By tracing what is suspended within it, what seems like a painted sky is often a map of dust, smoke, and ice, arranged in layers above the turning earth. Sunset does not end daylight at the moment the sun disappears below the horizon. Even after the solar disk is no longer visible, the sky often remains bright enough for outdoor activity. Landscapes retain form, and colors continue to shift. This interval is known as twilight, the gradual transition between day and night. Its first stage is called civil twilight. Civil twilight begins when the center of the sun moves just below the horizon and continues until it reaches approximately 6 degrees beneath it. Though the sun is hidden from direct view, its light still enters the upper atmosphere and is scattered downward toward the surface. The observer stands in Earth's shadow, yet the sky remains illuminated by air above and beyond the horizon that is still receiving sunlight. This explains why streets, fields, coastlines, and buildings often remain visible after sunset. Enough scattered light persists to support many ordinary activities without artificial illumination, especially under clear skies. Historically, This practical usefulness gave civil twilight its name, as it marked a period when civil life could continue in natural light. The colors of this stage are often subtle and layered. Near the horizon, warm tones may linger where sunlight travels longest through the atmosphere. Higher overhead, deeper blues begin to form as direct daylight fades and scattered shorter wavelengths dominate the remaining illumination. The contrast between these zones can be gentle and expansive. Clouds frequently become more noticeable during civil twilight. High clouds may continue reflecting warm sunlight even after the ground darkens, while lower clouds sink into gray shadow. The thin cirrus can glow pink or gold for several minutes, depending on altitude and atmospheric clarity. The duration of civil twilight varies with latitude and season. Near the equator, the sun descends more steeply relative to the horizon, so twilight is often brief. At higher latitudes, especially in summer, the sun moves along a shallower path, and twilight can last much longer. Weather also matters. Dust, haze, humidity, or smoke can brighten and extend twilight colors by scattering light more broadly, while thick cloud may shorten the visual transition. Civil twilight demonstrates that sunrise and sunset are not precise moments, but gradual processes governed by geometry and atmospheric optics. The sun may be below the horizon, yet its influence continues through the illuminated air above. What appears after sunset is not leftover daylight. It is sunlight still traveling through the atmosphere from beyond the edge of Earth. After civil twilight fades, the sky enters a quieter second stage, known as nautical twilight. During this period, the sun lies between approximately 6 and 12 degrees below the horizon. Direct sunlight no longer illuminates the lower atmosphere strongly enough to preserve ordinary daytime brightness. Yet enough scattered light remains in the upper sky to create a clear separation between sea, land, and horizon under favorable conditions. The name comes from navigation. Historically, sailors could still distinguish the horizon from the darkening ocean and use visible stars for orientation during this interval. It is a transitional light level, too dim for day, not yet fully night. Visually, nautical twilight is often defined by a deepening gradient of blue. Near the horizon, a faint band of residual light may persist, sometimes carrying traces of silver, pale green-blue, or muted amber, depending on atmospheric conditions. Above it, the sky darkens steadily into richer cobalt and indigo tones. Higher still, the first brighter stars and planets begin to stand out against the fading glow. This layered appearance results from geometry. Although the sun is farther below the horizon, it still illuminates higher regions of the atmosphere. Those upper layers scatter remaining sunlight downward, while lower layers have already entered Earth's shadow. The observer sees different altitudes of atmosphere transitioning at different times, creating smooth vertical changes in brightness and color. Blue tones often dominate because the warm direct beam has largely vanished, while shorter wavelengths continue to contribute strongly to scattered skylight. At the same time, overall intensity is much lower than during daytime, so colors appear cooler and more subdued. Clouds become silhouettes or faint reflective surfaces during nautical twilight. High, thin clouds may briefly hold residual color, but most lower clouds darken into soft shapes against the remaining sky glow. Water surfaces can mirror the gradient, turning bays, lakes, and oceans into dark plains edged with light. The duration of nautical twilight depends strongly on latitude and season. In tropical regions, it may pass quickly. At higher latitudes, especially in summer, the sun descends shallowly, and this stage can linger for extended periods. Nautical twilight reveals the atmosphere as a layered volume, losing sunlight from below upward. The sky does not switch suddenly from bright to dark. It descends gradually through shades of blue, each level marking the retreat of solar illumination behind the curve of Earth. As nautical twilight deepens, the sun continues to sink farther below the horizon. When it reaches approximately 12 degrees beneath it, a final transitional stage begins, astronomical twilight. This interval lasts until the sun is about 18 degrees below the horizon, after which the sky is considered fully dark in the astronomical sense. By then, scattered sunlight is diminished enough that most faint celestial objects can be observed clearly under suitable conditions. Astronomical twilight is the last trace of day remaining in the atmosphere. The sun is far from direct view, yet its light still reaches the highest layers of air above distant parts of Earth. Those upper regions scatter a small amount of illumination toward the observer, creating a faint residual glow. As the sun descends further, that glow steadily weakens. To the eye, the western horizon after sunset or eastern horizon before sunrise may still show a subtle gradient, shifting from dim blue-gray near the horizon to darker tones overhead. Compared with earlier twilight stages, color becomes restrained and delicate. The vivid golds and reds of sunset are gone, and even the cobalt blues of nautical twilight begin to dissolve into charcoal and black. This is also the period when the night sky gradually reveals its full structure. Bright planets are usually visible earlier, but during astronomical twilight, increasing numbers of stars emerge. The Milky Way, where skies are dark enough, begins to separate from the background. Faint nebulae, galaxies, and low-contrast celestial detail become easier to detect as atmospheric brightness declines. The exact duration varies greatly with latitude and season. Near the equator, the sun descends steeply, so astronomical twilight may be relatively brief. At high latitudes in summer, the sun can remain too close to the horizon for full darkness to occur at all. In such places, night may remain permanently twilight for weeks. Atmospheric clarity also matters. Dust, humidity, smoke, or urban light pollution can brighten the sky and obscure the subtle transition, making true darkness harder to perceive even when the sun is sufficiently low. Astronomical twilight demonstrates that darkness itself is gradual. Night does not arrive at a single moment. It returns layer by layer as the atmosphere stops receiving scattered sunlight. What we call night begins only after the last visible influence of the hidden sun has faded from the sky. Shortly after sunset, and sometimes just before sunrise, a subtle atmospheric display can appear opposite the sun. Low above the horizon, a broad dark blue-gray band slowly rises after evening sunset or descends before morning dawn. Above it, a soft pink or rosy arc may glow across the sky. These paired features are known as Earth's shadow and the belt of Venus. Despite the poetic name, the belt of Venus has no direct connection to the planet Venus, though Venus may occasionally be visible nearby. The term refers to the pinkish band that forms above the shadowed horizon during twilight. Together, these two layers reveal the geometry of Earth, sunlight, and atmosphere with unusual clarity. Earth's shadow is exactly what it sounds like. The planet, blocking direct sunlight from reaching part of the atmosphere behind the observer. After sunset, the sun lies below the western horizon, and Earth casts a vast shadow into the eastern sky. The lower atmosphere opposite the sun falls into darkness first, appearing as a broad blue-gray wedge or band rising upward as the sun sinks further. Above that dark region, higher layers of atmosphere are still illuminated by sunlight. The light reaching them has traveled a long atmospheric path, where shorter wavelengths have been scattered away. What remains is enriched in reds and oranges. When this worn light is then scattered through the upper air and blended with cooler background tones, it often appears pink, mauve, or rose-colored to the eye. This is the belt of Venus. The display is easiest to notice where the horizon is clear and open, over oceans, plains, deserts, or mountain viewpoints. Open skylines, thick haze, or dense cloud can obscure the contrast. Under very clear conditions, the boundary between the dark shadow and rosy band can appear strikingly smooth and expansive. As twilight progresses, Earth's shadow rises higher and the belt of Venus fades. Eventually, both dissolve into the broader darkness of evening. Before sunrise, the same process occurs in reverse as the shadow lowers and daylight returns. This phenomenon is a reminder that sunset is not only happening where the sun has disappeared, it is also visible across the opposite sky through the shadow cast by the planet itself. Few daily events reveal Earth's spherical form so gently. In the quiet colors of twilight, the planet's own shadow becomes visible in the air above us. Twilight does not last the same amount of time everywhere on Earth. In some regions, evening light fades quickly and darkness follows soon after sunset. In others, the sky remains luminous for long periods, with extended gradients of blue and lingering glow near the horizon, lest of which they come from the final regions from the south. These differences are caused primarily by geometry, the angle at which the sun moves relative to the horizon as Earth rotates and orbits the sun. Earth spins once each day, creating the apparent motion of the sun across the sky. But the sun's path is not identical at every latitude. Near the equator, the sun tends to rise and set along a steeper angle relative to the horizon. This means that after sunset, it drops below the horizon more directly. Because it reaches deeper twilight angles quickly, the transition from day to night is often relatively short. At higher latitudes, the sun's path is shallower. Instead of descending steeply, it moves diagonally along the horizon. After sunset, it sinks more slowly beneath it. As a result, the atmosphere continues receiving scattered sunlight for a longer time, extending civil, nautical, and astronomical twilight. Season changes amplify this effect because Earth's axis is tilted. During summer in either hemisphere, the local sun path becomes especially shallow at higher latitudes. Twilight can then persist for many hours. In far northern or southern regions, the sun may not descend far enough below the horizon for full darkness at all. This creates phenomena such as white nights and prolonged luminous evenings. During winter, the sun's path becomes steeper, shortening twilight in many of those same places. Seasonal contrast can therefore be dramatic, with the same city experiencing brief winter dusk and long summer twilight. Atmospheric conditions also influence perceived duration. Dust, haze, humidity, snow cover, and cloud layers can brighten the sky after sunset by scattering remaining light. Mountains or urban skylines may block low-angle glow and make twilight seem shorter. Open coastlines and plains often reveal it more fully. Human adaptation plays a role as well. Eyes gradually become more sensitive in dim light, allowing twilight to feel longer as stars emerge and landscape details slowly fades. Twilight is therefore not a fixed clock interval. It is the result of planetary orientation, latitude, season, and atmospheric clarity working together. When some evenings seem to linger or others vanish quickly, the cause is not chance. It is Earth's geometry turning sunlight across different horizons. Not all sky color changes are gentle transitions between blue day and warm sunset. At times, approaching storms transform the atmosphere into something darker, stranger, and more complex. Light becomes dim in mid-afternoon. Clouds take on heavy gray layers. In some severe weather conditions, portions of the sky may even appear green. These events can feel unusual, yet they arise from understandable interactions between sunlight, cloud structure, and suspended water. Storm clouds are fundamentally different from clear air or thin cloud layers. Large convective systems, such as thunderstorms, contain deep vertical towers of water droplets, ice particles, hail, and turbulent air extending many kilometers upward. Instead of allowing sunlight to pass relatively freely, these clouds absorb, scatter, and block large amounts of incoming light. The result at ground level is often a sudden reduction in brightness and a shift toward cooler or muted tones. The darkness beneath storms is partly geometric. Thick cloud bases intercept sunlight before it reaches the surface. Multiple scattering within dense cloud layers redirects light in many directions, while sun is reflected back upward or trapped within the cloud body. Areas beneath the heaviest cores may appear almost twilight-like during daytime. Green skies are less common and usually associated with intense thunderstorms. The color is not produced by a green substance in the air. It emerges from a combination of factors. Deep storm clouds containing abundant water and ice can filter and scatter incoming light in complex ways. When warm, low-angle sunlight, already rich in reds and yellows, passes beneath or through blue-gray cloud layers, the mixed result may be perceived as greenish. Large hail-producing storms often have strong vertical depth and dense precipitation regions, conditions that can enhance this effect. The visual association between green skies and severe weather is therefore indirect. Both may stem from the same powerful storm structure rather than one causing the other. Rain curtains, virga, and illuminated cloud edges add further variation. Sunlight striking one side of a storm while another remains shadowed can create dramatic contrasts of silver, charcoal, violet gray, or amber. Local terrain and time of day matter as well. Evening storms more easily produce unusual color because sunlight is already filtered by a long atmospheric path. Storm light reminds us that the atmosphere is not a thin decorative layer, but a three-dimensional fluid system capable of reshaping daylight within minutes. When skies darken or turn green before a storm, it is the visible signature of thick cloud atmospheres reorganizing the passage of light. In many high mountain regions, the daytime sky can appear deeper, darker, and more saturated blue than it does at sea level. Travelers often notice this change immediately. Above alpine valleys, desert plateaus, or elevated volcanic landscapes, the sky may seem unusually clear, with strong contrast between bright sunlight and dark blue overhead. This effect is not imaginary. It arises from altitude, reduced moisture, and the changing optical thickness of the atmosphere. At higher elevations, an observer stands above a portion of the atmosphere that would normally lie overhead at lower altitudes. Air pressure decreases with height, meaning there are fewer gas molecules above the mountain than about a solar slope and part of a coastal plain. The total column of air through which sunlight must pass becomes smaller. With less atmosphere above, there is often reduced broad scattering from haze, aerosols, and water-rich lower layers. The sky can therefore lose some of the whitish softness commonly seen near humid lowlands. The remaining scattered light may appear more strongly blue, especially when viewed overhead, where the path through air is shortest. Dry air is especially important. Many mountain climates have lower humidity than nearby lowlands, particularly in continental interiors or rain shadow regions. With fewer water droplets and less moisture growth on aerosol particles, knee scattering is reduced. This allows clearer visibility across long distances and preserves stronger color contrast in the sky. The darker blue, often noticed near the zenith, also reflects reduced diffuse light overall. Because less atmosphere is available to scatter sunlight broadly, the sky can appear less bright while remaining intensely colored. Against this background, clouds, snowfields, and sunlit rock may stand out sharply. Ultraviolet radiation also increases with altitude because there is less atmosphere to absorb and scatter it before reaching the surface. Though invisible to human eyes, this contributes to the sense that mountain sunlight is harsher or more direct. Shadows can feel crisp, and exposed skin may burn faster than expected. Even so, the sky does not become black as it does in space. Mountains remain far below the altitude where most atmospheric scattering disappears. There is still ample air above to produce a blue sky, just a thinner and cleaner version of it. High mountain skies reveal how strongly everyday color depends on the thickness and composition of air above us. When the atmosphere becomes drier and shallower, the blue of day often grows deeper. Near Earth's polar regions, the daily movement of light differs profoundly from the familiar rhythms of lower latitudes. In temperate and tropical zones, the sun rises, climbs, descends, and sets in a relatively regular arc. But near the Arctic and Antarctic circles, the sun often moves at shallow angles around the horizon, especially during spring and summer. This creates long-lasting twilight, unusual sky colors, and seasons where daylight itself behaves in extended forms. The cause is Earth's axial tilt. The planet rotates on an axis inclined by about 23.5 degrees relative to its orbit around the sun. As Earth moves through the year, each hemisphere alternately tilts toward and away from the sun. At high latitudes, this geometry strongly changes the sun's apparent path across the sky. During polar summer, the sun may remain above the horizon for 24 hours or more, producing the midnight sun. Even when it stays low, it circles the sky rather than rising high overhead. Because sunlight arrives at shallow angles, it passes through long atmospheric paths for much of the day. This often creates sustained golden light, soft reds near the horizon, and extended bands of blue above. Conditions that elsewhere occur only at sunrise or sunset can persist for hours. During polar winter, the opposite extreme develops. The sun may remain below the horizon for weeks or months, depending on latitude. Yet complete dark, it can be so stupid. Long twilight periods can still occur,
when the sun approaches but does not cross the horizon.
The sky may brighten into deep cobalt, violet, or pale amber bands, even at midday. Snow and ice add further optical effects. Bright surfaces reflect large amounts of light back into the atmosphere, increasing overall luminance and extending the visual reach of twilight. Clouds over snowy terrain can glow softly from reflected light below, while clear air often allows sharp gradients between illuminated horizon and dark overhead sky. Cold polar air can also be exceptionally clean and dry, reducing haze and revealing subtle atmospheric colors with unusual clarity. Under certain conditions, ice crystals create halos, sundogs, pillars, and luminous arcs around the low sun. These regions show that daylight is not simply on or off. It can stretch, bend, and linger according to planetary geometry. In polar skies, the angle of sunlight becomes the dominant artist, painting long seasons of dawn and dusk across the edges of the world. Most sunsets are shaped by local weather, humidity, dust, and ordinary atmospheric aerosols. Yet at times, a single geological event can alter evening skies across entire continents. Major volcanic eruptions are among the few natural processes capable of changing global sunset color for months or even years. When volcanoes inject fine particles high into the atmosphere, the effects can spread far beyond the eruption itself. Explosive eruptions can send ash, gases, and aerosols upward through the troposphere, and, in the largest cases, into the stratosphere. This upper layer of the atmosphere is especially important because it is dry, stable, and experiences less vertical mixing than lower air. Particles that reach it can remain suspended for long periods, circulating around the planet through high-altitude winds. Not all volcanic material has the same optical role. Heavy ash often falls out relatively quickly near the source. Finer particles and sulfur dioxide gas can have wider consequences. Sulfur dioxide may react chemically to form sulfate aerosols, tiny droplets or particles highly effective at scattering sunlight. These aerosols can persist aloft and modify how light travels through the atmosphere worldwide. During sunrise and sunset, when sunlight already moves through a long atmospheric path, these additional particles become especially visible. Shorter wavelengths are scattered more strongly, while red and orange tones can intensify across broad sections of sky. Afterglows may linger longer than usual, with luminous crimson bands, purple horizons, or bright twilight layers appearing well after the sun has set. Historical records describe remarkable sunsets following major eruptions. Artists, sailors, and scientists have all noted unusual skies after events such as Krakatoa in 1883, Pinatubo in 1991, and other large eruptions. Paintings from certain periods may even preserve atmospheric evidence of volcanic aerosols through their sunset colors. Volcanic particles can also cool climate temporarily by reflecting part of incoming sunlight back to space. Thus, the same aerosols that enrich sunsets may simultaneously reduce global surface temperatures for a time. The visual effects gradually fade as particles settle out or are chemically removed from the atmosphere. Months later, sunsets often return to more ordinary patterns. Volcanic sunsets remind us that the sky is connected to the solid earth below. A mountain can erupt, and distant evenings may change. When horizons glow unusually vivid across the world, the cause may begin deep underground, where geology has entered the atmosphere. By the end of each day, the sky may seem to have simply passed through familiar colors and returned to darkness. Blue morning, bright new, fading twilight. Because this sequence repeats so often, it can appear ordinary. Yet every stage is the visible outcome of physical laws acting through a planetary atmosphere in real time. The gloom of daytime is not painted overhead. It emerges as short wavelengths of sunlight are scattered by molecules smaller than the light itself. The pale horizon, deeper zenith, and changing brightness across the sky reveal differences in viewing distance, particle concentration, and atmospheric depth. Even a cloudless afternoon contains gradients shaped by geometry and optics. White clouds are not white by nature, but collections of droplets and ice scattering many wavelengths together. Gray storm bases show where light is blocked or repeatedly redirected within thick cloud layers. Haze softens landscapes because aerosols broaden scattering and reduce contrast. A mountain sky darkens because less atmosphere lies above the observer. Sunrise and sunset are records of long atmospheric pathways. As sunlight crosses greater thicknesses of air, blue wavelengths are increasingly scattered from the direct beam, allowing reds, oranges, and golds to dominate. Dust, smoke, humidity, and volcanic aerosols can strengthen, mute, or reshape those colors from one evening to the next. Twilight continues the story after the sun has disappeared. Civil, nautical, and astronomical twilight mark the progressive retreat of sunlight from different atmospheric layers. Earth's own shadow rises opposite the sunset, while the belt of Venus glows above it. In polar regions, shallow solar angles stretch these transitions across hours or seasons. What appears above us is therefore a continuous environmental measurement. Without instruments, the sky reveals moisture, particles, cloud structure, altitude, season, latitude, and the position of the sun. It displays the interaction between radiation from a star and gases surrounding a rotating planet. Human life has long depended on reading these signals for navigation, agriculture, weather judgment, and timekeeping. Modern science explains the mechanisms, yet the daily experience remains immediate and accessible to anyone who looks upward. The sky changes color every day because Earth is active every day, turning, orbiting, circulating air, lifting dust, forming clouds, filtering light. To watch the sky carefully is to watch physics made visible, written across moving layers of planetary air. And so, the sky returns to darkness, as it always does. Yet after seeing the science behind its colors, it may never feel ordinary again. Every blue afternoon, every pale horizon, every red sunset, and every fading twilight is the visible result of light meeting air on a turning planet. Above us, physics is always in motion, quiet, continuous, and vast. If you enjoyed this journey through the atmosphere, please subscribe to Physical Depth, like this video, and share it with others who look upward in wonder. Until next time, thank you for watching.